Hello again, it's me, Professor Albert, here again with lesson 21. Let's learn some econ. So today we're going to do the much anticipated task of actually mathing out how you find the contract curve, i.e. the point of all of the Pareto optimal points. And we're going to show you how intuitively you can find the contract curve in the weird situations where things are not perfectly Lagrangeable. So let's do it. So as a recap, we're looking at Edgeworth boxes. These are basically just a way in 2 dimensions to show how goods have been allocated to 2 different people when you have 2 goods, fixed quantity of goods, and they each have their own preferences. And it's all represented like this. We saw on a graph that the contract curve is the set of points at which they no longer can gain from trade. That is, at points A, B, F, C, D, and G, the 2 individuals cannot in any way make one of them better off without harming another, and therefore these are the Pareto optimal point. They are found graphically by looking for where the 2 indifference curves are tangent, i.e. at point B, the indifference curves are tangent. Why does tangency matter? Well, at points that are not tangent, like E, the indifference curves will overlap and create a lens, given by this blue region, and in that lens, all of these points are strictly better for one or both individuals. Whereas at B, F, and C, there is no lens. They're doing the best that they can. So, the question is, if we want to find all of these points along curve A through G, what do we have to do? The question I would ask yourself is, what are we maximizing and what is our constraint? Give it a think. Come back. So, in short, there are 2 equivalent ways to solve this. One, we could say that point B is making Jane as happy as possible without making Denise miserable. Alternately, we could say that point B is making Denise as happy as possible without making Jane miserable. I.e., there's a trade-off. The contract curve gets us points that are as good as possible for one person without harming the other. So let's just say we have some generic U function. Could be anything. And let's say that we have utility of Jane such that Jane only cares about her good 1 and her good 2. Denise's utility only depends on her good 1 and her good 2. So let's say we want to maximize Jane's utility. What then must be true about Denise's utility? How do we represent not making Denise miserable? Well, to me it seems like we want to do max U of J such that U of D is at least some number. Let's just call it U bar, some fixed level of utility. So we want to max Uj such that UD is better than or equal to U bar. You'll note that since there's non-satiety, we can just reach U bar, right? If ever we were to give Denise more than the requisite U bar utils, that would mean we can make Jane a little better. So we're going to actually be able to use the equality constraint by the same argument we used when we did the expenditure min and budget problems for consumers. So we're maximizing Jane's util subject to Denise getting some fixed amount of util for herself. Are there any other constraints? Give it a think. Welcome back. Yes, there are. Give it another think. We also have to obey the endowments. Like in the original example, we cannot give Jane and Denise combined more than 80 units of candy. We cannot give Denise and Jane combined more than 50 units of good. So we actually have 2 additional constraints regarding the total amounts of wood and candy being given. So note we should actually have these 2 constraints. You will note, however, that these constraints can be rewritten. That is, you'll note that QD1 equals Q1, that's a number, minus QJ1, i.e. as well, QJ2 plus QD2 equals Q2 implies QD2 equals Q2 minus QJ2. So we're going to put this all together. We're saying we want to maximize Jane's utility subject to Denise, whose utility is a function of QD1, QD2, being at least some U bar. You'll note that I have rewritten Q1 for Denise as Q1 total minus QJ1, and I've written QD2 as Q2 minus QJ2. The reason we have rewritten QD1 as this and QD2 as this is because now we only have two variables, QJ1 and QJ2. QJ1, QJ2. If I were to leave these as functions of D, we would have to maximize our Lagrange subject to Q1, Q2, lambda, QD2, QD1, and that's a lot harder. So always remember when you're trying to find the contract curve to substitute in your Q's subject to the original quantity in the universe constraints that you only have one person's variables in the Lagrange function. All right, now that we have the Lagrange function, what are we going to do? Hopefully, you said, take first order conditions. And that's right. The first FOC will just be how does Jane's util depend on her good one. Second will be how does Denise's util change dependent on Jane's good one. Same for good 2. And the third constraint third condition as always is our constraint, namely that Jane gets at least enough util. My question next is, why would Denise care about Jane's util? I said that Denise had a utility function that was QD1, QD2. I.e. there are no QJ terms in here. Therefore, why is this not 0? Give that one a think. You will note this is not 0 because all goods are allocated to either Jane or Denise. Therefore, if we give Jane any wood or candy, Denise will lose wood and candy at exactly the inverse rate that we gave it to Jane. So therefore, although Denise, in a world of no limits, would not care if Jane had anything, Denise does care that she has things. And since the goods sum to whatever the original total was, that means Denise likes Jane not to have things, because that means she has things. Cool. So we would take these FOCs, and as always, use the lambda term to combine these, and you will find that these simplify to saying that MRS for Jane equals MRS for Denise. Hey, wait! That's what we said we'd get from the start, right? We said this contract curve was defined as where the indifference curves are tangent. What's the slope of an indifference curve? The MRS. So this means our contract curve must be found at all points that our MRSJ equals our MRSD. So the rest of today you should spend working through a few exercises, carefully curated, so that you can practice your ability to find contract curves under normal and less than normal situations. First, we have the most typical problem, one where both Jane and Denise have Cobbs-Douglas utilities. In this one, find the correct Lagrange function and take the first order conditions. You can continue past the first order conditions to solve if you want, but it's a lot of algebra, sounds like a lot of work. Then, repeat this exercise, but instead we're going to start using wonky utility functions. Give Jane the utility function qj1 plus qj2. Give Denise the min function of d1 and d2. And lastly, try it with both of them having linear utility functions. Good luck. Let me know how it goes. Bye.